Welcome for the lecture on digital signal processing. Today we'll be learning long data filtering through block convolution. In last lecture I have already explained the linear convolution can be also obtained through circular convolution way, and the procedure is we initially make length of both the sequences equal to the length of output which will be resulted if I perform linear convolution of these two. So if this is having n1 samples, this x2n having n2 samples, then the linear convolution will have n1 plus n2 minus 1 number of samples. So we will add additional zeros at the end of sequence x1 and zeros at the end of sequence x2 to make both of length n1 plus n2 minus 1, and then I perform circular convolution either in a time domain or in frequency domain using DFT IDFT method. I will get result y of n which will be same as the result as if we perform the linear convolution of sequences x1n and x2n. So with that understanding, we'll see what long data filtering is. In many applications, the input signal is of indefinite duration. We don't have that much amount of memory to store that data, and no filtered samples can be calculated before we collect all the input samples. So we have to wait till we collect all the input data samples, and implementing FFT for such a large number of points is impractical. So the solution is provided by using block convolution. In block convolution, we segment the incoming input into partitions each of equal length, and we perform individual convolution of that partition with impulse response which is of finite, typically small length, and outputs resulted by convolving those individual partitions will be fitted together in an appropriate way so that the result will look like the lengthy input sequence is as if convolved directly with the small impulse response. Though it is not directly convolved, but the result will look like as if it is directly convolved. So the methods that can be used are overlap save method and overlap add method. The name is intuitive. Overlap save means we'll overlap the input sequences, and when we'll perform convolution, we'll save some of the samples, we'll discard some of the samples. And in second method, we'll overlap input sequences, and at the end when we get output partitions, we'll add some of the part of those output partitions to get the desired result. So we'll see in detail how it is done. It's important to note that if an L point sequence is circularly convolved with M point sequence where M is less than L, then the first M minus 1 samples are incorrect when it is compared with the linear convolution result of these two sequences. What do I mean? If you look at this sequence X of n, this has L number of samples. Here L is equal to 5, and this has 2 samples, that is M is equal to 2. So L is greater than M. When we circularly convolve these two sequences, we get this result which is 13, minus 10, minus 13, minus 16 and minus 19. Now if I look at what is actual linear convolution of these two sequences by using the standard way of finding linear convolution, some trick. If I compare this result with result obtained by using direct circular convolution of those two sequences, I see that the minus 19 output sample is available here, minus 16 output sample is available here, minus 13 is also available, minus 10 is also available, but the actual result minus 7 is not being represented as minus 7, instead it is 13. So that is incorrect result. So what I said, M minus 1 samples will be incorrect. So this is that sample which is incorrect. in this case m is equal to 2, so one sample is incorrect. And obviously this sample is missing here because initially before performing circular convolution we have not adjusted the length of both the sequences to be equal to length of output. So if we do that, we directly get the linear convolution. That is not a problem. So in a first method, that is overlap save method, we will have input x of n of arbitrary length. We will have an impulse response h of n of capital M number of samples, typically small, and we have to partition the input sequence into multiple sections with each containing capital L number of samples in such a way that L is greater than M and L plus M minus 1 should be equal to the size of DFT that we are going to compute. Sometimes that size of DFT may be specified depending on the capability of a hardware or software. So if capital N is known, we can find L as N minus M minus 1. If capital N is not known, we can assume any L value which is greater than M. The procedure of overlap save method goes like this. First, we determine number of samples in the impulse response, we call it as a M, and we find what is M minus 1. Then we look for whether capital N DFT size is specified. If it is specified, we'll use that to find partition size of that input data, that is capital L. And already I told you, if capital N is specified, we'll have N is equal to L plus M minus 1. If capital N is not specified, we'll choose capital L at least greater than M by 1. So we'll partition the input sequence with small blocks each of length L, and if last block has less than L samples, then we will fill those samples with 0 to make last partition size also equal to L. In step 4, we make length of impulse response h of n is equal to n by padding L minus 1 zeros to the impulse response h of n. So now what we have? We have input partitions of each length L and the impulse response of length capital N. So to perform circular convolution of these two and to get the result as if it is a linear convolution result, what we want is, we want both the lengths of impulse response and each input partition to be equal to N. So for that, we have to add some samples in each partition of input sequence so that length becomes capital N. So we make that length capital N by padding extra M minus 1 samples at the beginning of each partition as shown below. Now suppose this is the input sequence which is partitioned with L samples each. Suppose in last partition we don't have L samples, so what we will do is we will add extra zeros to make this length also equal to L, and after that we will pad extra M minus 1 samples at the beginning of each of this block. So we will do like this. In the first block, x1 of n will be formed by padding M minus 1 zeros at the beginning of first partition. Actually, we will try to copy last M minus 1 samples from the previous block and we'll paste those M minus 1 samples at the beginning of next consecutive block. So here there is nothing before this sequence starts, so we assume that all the samples before this are 0, so we copied M minus 1 zeros. After that, we'll copy last M minus 1 samples from x1n and we'll paste it at the beginning of second partition. That completely becomes my second sequence x2n. Again, I will copy last M minus 1 samples from x2n and I will paste at the beginning of third partition, that will become my third sequence x3n, and I will keep on doing this till there is no partition left. In a step 6, each of these individual sequences x1n, x2n, x3n and x4n are individually circularly convolved with impulse response h of n to obtain results y1n, y2n, y3n and y4n. Now, as each input sequence and impulse response are of length capital N, each of these outputs y1 to y4 will have capital N number of samples. And if I arrange them one after other as it is, like y1, y2, y3, y4 so on, it will not give me the result which is same as linear convolution, because at the beginning we made some adjustment in a input sequence, like copying m-1 data samples at the beginning of each partition. So we have to remove or nullify that effect while forming the output also. So what we will do is, as we saw in second slide, when I perform circular convolution of L point sequence with M point sequence, where L is greater than M, actually m-1 data samples at the output are incorrect. What we will do is, we will use a strategy of removing first m-1 samples from each data block. So here step 7 will be discard initial m-1 output samples from each block and arrange the remaining samples one after other. So this is my complete y1n, this is complete y1n, this complete box. From that, initial m-1 data samples are to be discarded and remaining samples are simply copied down. Then from a next output block y2n, will again remove first m-1 samples and remaining samples I will simply copy down. I will keep on doing this and I will keep on copying remaining samples from each of those output blocks, and that will become my output frame, whose effective length will be length of x of n plus length of h of n minus 1 number of samples. As an example, we'll look at this sequence x of n with 10 samples and h of n with 3 samples. Now, by logic, the linear convolution of these two sequences should result in 10 plus 3 minus 1, that is 12 number of samples. Capability of processor and speed will decide the DFT size. Let capital N, that is DFT size, is specified for this particular example and it is equal to 5. According to the procedure of solving overlap save example, the first step is to see what is capital M. Now in this case, capital M is equal to 3 samples. Then we'll see what is size of DFT, that is equal to 5, which is specified. In third step, we'll see the partition size for the input sequence. So we have L plus M minus 1 is equal to N. We plug in N is equal to 5 and M is equal to 3. Here we see that the partition size should be equal to 3. Now in step 4, we have to pad L minus 1 zeros at the end of impulse response to make its length equal to N, that is equal to 5. So we padded L is equal to 3, so we padded L minus 1 is equal to 2 zeros at the end and we made length equal to 5 samples. Step 5 is to make each partition of size capital N is equal to 5. Now if I show you actual sequence, it is 3 minus 1 0 1 3 2 0 1 2 and 1. This is the input sequence. If I make partition of 3 samples each, it will look like this: 3 samples, 3 samples, 3 samples, and here I have only 1 sample. So as I said, if last partition has less than L samples, we can consider extra zeros to make length equal to L. and after that we have to make length of each of those partitions to be equal to capital N, that is equal to 5. So in first partition we'll pad m-1 zeros at the beginning to make input partition of size n samples, and we call it as a x1 of n. While preparing for the second partition, we'll copy m-1 samples from a x1n, last m-1 samples from a x1n, and we'll place them at the beginning of next partition, that will become my x2 of n. So we copy these last m-1 samples, that means 2 samples, and I'll place them here, and that becomes x2n. Similarly, we'll copy last m-1 samples from x2n, we'll place them at the beginning of this next partition, that will become x3n. Similarly, x4n. As I said, if length is not L, make it L by padding zeros. So we have these 4 input sequences, x1n, x2n, x3n and x4n, to be circularly convolved individually with the impulse response h of n. So we'll do that. Xk of n, each individual x of n is circularly convolved with h of n. These both the sequences have length 5 each. So output also will have 5 samples. So we have these 4 output blocks. Now to arrange these output blocks, we have to discard first m-1 samples. So after discarding first m-1 samples, we have to copy down remaining samples as it is, one after other. So you can see here, the first sequence y1n has samples -1, 0, 3, 2, 2. If I discard first m-1 samples, m is 3, so m-1 is 2. So if I discard these 2 samples, remaining samples 3, 2, 2 will be copied down as it is. Similarly, from second sequence, I will discard sample 4 and sample 1, and remaining samples will be copied down. From third, I will discard sample 6 and sample 7, remaining is copied down. And from fourth output block, we will discard 1 and 3 and will copy 4, 3, 1. So that becomes my output of length 12 samples, which will be equivalent linear convolution of input sequence x of n with h of n. In a second method of block convolution called as overlap add method, the procedure will be somewhat similar, some common steps, but only few differences. So we'll have an input sequence x of n of arbitrary length, typically long sequence, h of n typically small with capital M samples. X of n is to be partitioned with L samples each in such a way that capital N is equal to L plus m-1. Up to this it is same. So in a procedure, we see that in step 1 we determine m and m-1. Step 2 is also same. We see what is DFT size capital N. In a step 3 we partition the input sequence into blocks of each length L samples. If last partition has less than L samples, then we pad extra zeros to make length equal to L samples. In step 4, we pad L-1 zeros at the end of h of n to make its length equal to capital N. So 4 steps are same. 5th step is little different. In overlap save method, we made adjustment at the beginning of each partition to make length of each sequence equal to n samples. Here we will do adjustment at the end of each partition to make length equal to capital N samples. And that adjustment is simply pad m-1 zeros at the end of each partition, and that makes a complete n length sequence x1n, x2n, x3n and x4n. If there are any more samples, we'll have more number of sequences. After doing that, we'll perform individual circular convolution of those sequences with impulse response to get outputs of each length n samples. Again, as I said, these outputs need to be arranged in such a way that the result should look like a linear convolution result. So that strategy is, we overlap last m-1 data samples of a previous block with first m-1 data samples of a next block, and we add them. We keep on doing this for each consecutive data partition till we left with no more partitions. So here we'll overlap y1n with y2n for m-1 data samples like this. Similarly, last m-1 data samples of y2 are overlapped with first m-1 data samples of y3, and we add them. Last m-1 data samples of y3 are overlapped with first m-1 data samples of y4, and we add them. And in between, if there are any more samples, left side m-1, right side m-1, if there are any more samples left in between which are not overlapped, we'll copy down those samples as it is. So here, these samples from here to here, these samples are simply copied. These m-1 data samples are added with these m-1 data samples here, and the results of addition will be stored here. These samples are copied as it is. Here addition result. Here these samples are copied as it is. Here addition result. And here these samples are copied as it is. These samples are also copied as it is, because there is nothing to add after this block. And we see that final block that is formed is a linear convolution of x of n and h of n. We'll see an example for this also. So this slide is same as the previous example slide, because first 4 steps are same. So we have capital M is equal to 3, we have capital N is equal to 5, we have length of each partition equal to 3. So we pad L-1 zeros at the end of h of n to make its length equal to 5 samples. After this, we'll partition the input sequence into L samples each, first, second, third, fourth, fifth, sixth, 7th, 8th, 9th and 10th sample. So this will be single sample, so we'll pad 2 more zeros to make its length equal to L samples. So we'll have these partitions. At the end of each partition, we'll pad m-1 zeros to make its length equal to capital N. And now we have x1n of length 5 samples, x2n of length 5 samples, and so on. All of these sequences have 5 samples. We'll circularly convolve these with impulse response h of n to get individual output blocks y1n, y2n, y3n and y4n. So these are the results after performing that circular convolution. Output blocks also has 5 samples each, and the additional strategy to arrange these outputs is to overlap and add m-1 samples for the consecutive blocks. So you can see here we have first output block as 322 -1 0. We overlap that with next data 14652. So m-1 samples have been overlapped. Last m-1 samples of y1 are overlapped with first m-1 samples of y2, and we add them. The result will be stored here. And this sample which is not overlapped with any other partition will be simply copied as it is. Next, we'll overlap m-1 samples of this with m-1 samples of next block, and we'll see that the result is 5 and 3. This is simply copied as it is. Here this will be added, result is 4, 3. This is simply copied down, and this is simply 0. So we see that the effective length of our output, which is linear convolution of x of n and h of n, will have 12 number of samples. So it verifies that in linear convolution the output length is equal to length of first sequence plus length of second sequence minus 1. Thank you.